Here you go. Yeah, thanks for having me. So this is a presentation largely based on a work I've performed with Andy Jackson at ETH, and you can read this paper for more information. And part of the work I'm going to be presenting is also based on the work of Daria, which is a PhD student at ETH. So our focus is in the geomagnetic field temporal variations on sort of decadal timescales. And as we have heard from previous talks, the geomagnetic field is generated by convective motions within the Earth outer core. In particular, we are talking about the possibility of reproducing and forecasting geomagnetic field variations. Now that is a seminar by itself. One approach to these is this called data assimilation, which is essentially what gives us meteorological forecasts. So you need a numerical model as realistic as you can of the Earth at the core, which should then correct somehow based on available observations, and which hopefully create an initial condition that is the best possible to then create a reliable forecast. So as we heard, the problem of doing so this has been done. The problem in doing that is the reliability of this forecast, and more specifically, the dynamical core, the numerical model that simulates the Earth at the core. As we heard, the Earth at the core is an extreme environment characterized by rapid rotation, low viscosity, and possibly, although it's a bit uncertain, but we think very strongly forced thermal forcing, and this we kind of know better, highly turbulent regime. So the separation in the parameter space between simulations and the Earth is depicted here. And numerical models geared for data simulation live not at the extreme deep of what we can do. And that's simply because these things require many iterations of numerical integrations. So you can't really just run the most extreme thing we can do. In particular, we're focusing on these separation, the Ekman number, which is a measure of viscosity of a rotation.
Stefano, can I just stop you for a minute? Are you going through your slide at the moment?
Oh gosh.
Because all we can see is your title slide.
I don't know. It's not showing. Sorry. Sharing is paused. I have no idea how this has been done. Okay, sorry. Just let's redo this. I do apologize for whatever happened.
Right. Okay.
I still have. So if I do this, you see the slides changing?
No.
Wow. Not sure why. Let's try something else. I really apologize. This is the first time I use Keynote, and not sure if that is the problem, but okay. Now they're changing, right? Okay. Sorry for that. Yeah. So again, yeah. So you have not followed what I was saying probably, but here it is. Rapid rotation, low viscosity, and strongly turbulent regime, the Earth. And yeah, you see on the right the separation. We are going to be concerned about separation in the Ekman number, which somehow we use it as a separation in terms of the rotational period between the Earth and what we can actually simulate. So this is a problem, but let's see if this can also help us. So this is the Navier-Stokes equation, non-dimensionalized. And as you can see, in a way that the Ekman number appears. So now we know the Ekman number is 10 to the minus 15. So everything that multiplies the Ekman number is probably small. Now that depends on how strongly forced the convection is, and how strong the magnetic fields are. But let's assume you can do that, and you are left with what we know as the geostrophic balance, which creates flows that are vertically invariant. Now, obviously, this is not all that is happening in the core, but we believe that the leading order, this holds. And indeed, 3D simulations of both thermal convections on the left and dynamo simulation on the right shows this tendency of flows to be aligned along the vertical direction. Now, yeah, the one on the left is a 3D simulation, so but it is purely of thermal convection, so there are no magnetic effects. But still, I hope I'm convincing you that at least in some circumstances, the flows are extremely columnar. So one approach to constructing models that are so-called quasi-geostrophic is to assume that. Let's just assume that the flow is columnar, plug it into the Navier-Stokes equation, and solve that problem. And this is an example of what Céline has done in a paper in 2019, and that allowed her and her collaborators to reduce the Ekman number quite drastically compared to 3D numerical simulations. So if this works so well, why do we need a new model, and why do we want to call it in a different way? So the main problem is when you want to consider magnetic effects. And in general, for now, for this talk, we're going to neglect diffusions. It's simpler, and we can discuss about that. So there are various approaches. One is leave that in 3D, and then just the common approach is to take the axial vorticity equation, so curve the Navier-Stokes equation, and then integrate it in the vertical. So you're left with terms of that kind, as you see. So you can just plug the 3D magnetic field in the Lorentz force, curl it and integrate it, and solve the result in 2D Navier-Stokes equation. This results in a hybrid model. We want to have everything in 2D just to do better, because that will allow you geometrical simplification that allows you to create more aggressive numerical models. Another idea was to assume that B has the same shape as the flow, so columnar. This results in a very elegant mathematical description, but is a bit restrictive, or at least we think it is. Another idea that is the starting point for our model is a bit complicated, but if you consider the magnetic field and the Lorentz force just through those three quadratic quantities, you obtain a closed system. The problem is that in doing so, you have to throw away surface terms in the Navier-Stokes equation, and although it's a sensible thing to do, it results in a system that is not well posed anymore. So this is the problem we want to tackle. Actually, we will start from this third option and bring it a step further. So our Plesio-geostrophic model works. I'm just giving you a very brief flavor of how you derive it. So common approach is curve the Navier-Stokes and then integrate. We do the other way around. This somehow gives us better control on the surface terms, and eventually we will solve them explicitly. So you do that first, but you are left with the pressure and surface terms that you don't want. And to delete those, you have to consider some more exotic things, such as the Navier-Stokes equation on the equatorial disk, or this kind of antisymmetric integral terms. Once you combine all these, you obtain something that looks kind of like an axial vorticity equation, or what you would obtain with that approach. And this term is the hydrodynamical term only. And the Lorentz terms, or in fact, this is a formula for every force in the Navier-Stokes equation, can be considered through this thing F through that formula. That means that you have control whatever variable you insert in those L tilde, L bar, and L naught, and that is somehow the complication. But you can do it. I'm going to show you what you end up with. It's quite cumbersome, but it's straightforward. You end up with these quantities. So you remember that I referred to some quadratic geomagnetic quantities. You have a bit more quantities around here that you need to control, but these all exact. You just have to solve these integrals through the induction equation, and you get some, these are the classical quadratic quantities. You get some antisymmetric quantities in which these weird objects appear, and you can control them explicitly though. These are the quantities that you have to solve on the equatorial disk, and at the end you are left with some surface term that you can explicitly control. So this is a bit daunting, but we have checked it somehow. First of all, we have checked the hydrodynamical part, just a couple slides of results, by reproducing what we call the inertial modes, so waves that are sustained by the rigidity imposed by the rotation itself. You can solve this analytically, in fact, and the solution compares quite well with the 3D expectation. So the order n is the azimuthal complexity, and as you increase n, you increase the radial complexity. And you see that they actually compare quite well with 3D. These are 3D modes, and they are columnar. So you have a very good agreement in terms of eigenmodes. And there are some regions in the space in which you have some departure in terms of eigenperiods, but it's quite good agreement, I would say. And finally, Daria has calculated magneto-hydrodynamics mode. So you can impose background magnetic field. We impose this field first, that has first done by Marcus. So there are known results that we could compare our solution with. And again, we reproduce the two fast and slow branches of linear solutions with, I would say, quite good agreement between the 3D expectation and our PG numerical calculations. And finally, you can look at the modes, at the eigenmodes, 3D versus PG, Plesio-geostrophy. And again, the structure is retrieved, I would say, very well, both the velocity-related quantities and so this is a meridional slice, and these are equatorial slices of these quadratic symmetric quantities and these more exotic things that we usually don't look at, but they are both reproduced quite well.
You've got 1 minute left.
Yeah, I'm done. So yeah, I've shown you these. Please, if you're curious, please check out the paper for more mathematical details. We have derived a system that is quite daunting, but I have to remark it is exact. Apart from the assumption of columnar flows, we are not making any assumptions anymore. We are not throwing away surface terms, and all variables are 2D, so there is still great computational gain from this system. We improved on previous columnar formulation that had problem once the magnetic field was considered. And the calculation of eigenmodes and analytic solution is quite encouraging to bring it to the next step, which is essentially consider more problems with known solution, validate our code more, and eventually time step the full nonlinear problem with data assimilation in mind. And yeah, thank you very much for your attention. I'm happy to take questions.